Section 4 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Abai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 3. The Evolution of Astronomical Instruments and Methods. The Rise of Astrophysics. The Spectroscope and its Modifications. To gain a knowledge of the composition and nature of the celestial bodies is the fundamental problem of astronomy. Unable to bring a celestial body or a specimen from it, except in the rare case of a meteorite, to the chemical laboratory for study, the astronomer is dependent entirely on a study of the energy that it emits in the form of light and heat rays. Strange as it may seem, these rays furnish as true a record of their birth and life history as if a sample from the distant star had been tested in the assay furnace or with the reagents of the chemist. The simple instrument called a spectroscope gives an accurate and permanent record which affords complete data for the studies of the astronomer. White light is composed of various forms of vibration, which, taken by themselves, will supply light of various colors from red to violet. It was found by Sir Isaac Newton, in passing a beam of white light through a prism, that not all of the rays are bent equally toward and away from the perpendicular, but that the amount of bending depended upon their color, or, as it is now termed, their wave-length and position in the solar spectrum. Thus, when he permitted a beam of white light, emerging from a hole in a shutter, to fall upon a prism in a dark room, he found that there was produced after its emergence a brightly colored band with the red at one end, where the waves were refracted the least, and shading through yellow and green to violet, where the waves were bent or refracted most. Consequently, if there were a source of light capable of furnishing one color, and that only, it would be obvious, wherever that color appears in the bright band produced by the prism, that it radiated from a particular source. Before 1753, a young Scotchman, Thomas Melville, noticed that when various compounds of sodium were introduced into an alcohol flame and viewed through a prism, there appeared a particular shade of yellow light, which was always bent or refracted to a fixed and definite degree. Others repeated these experiments, and finally Fraunhofer (1787 1826), a great optician of Munich, rediscovered this deep yellow ray and found its place in the spectrum. The same phenomenon was noticed by many other experimenters. Indeed, the omnipresence of the yellow light was often an embarrassment in spectral research. That this yellow line was due to sodium was pointed out by William Swan. Finally, it was noted that the distribution of sodium was so general and the prism test of its presence so delicate that its absolute exclusion was well nigh impossible. Before Fraunhofer's experiments, the round hole in the shutter of Newton had been supplanted by a slit or crevice about 1/20th of an inch wide, and the spectral band thus formed from sunlight was not only continuous, but free from overlapping images, so that the colors were shown in their purity, crossed by 7 dark lines. In the course of his experiments, Fraunhofer not only used the slit, but added to it the telescope of the modern spectroscope. He was surprised to find not merely 7, but thousands of dark transverse lines, many of which he mapped, counted, and designated by the letters of the alphabet. Not only did he examine sunlight in this way, but also the light of the moon and planets, and found that stellar spectra too were crossed by the same dark lines. In the case of certain stars there were even dark bands. He found that one, or rather a pair of solar lines which he had marked in his map with the letter D, coincided exactly with the yellow beam which accompanied incandescent sodium vapor. The coincidence was noted by Fraunhofer, but the explanation came in 1859 from the distinguished German physicist Professor Gustav Robert Kirchhoff (1824 1887). He it was who sent a beam of bright sunshine through sodium vapor and discovered that the D line of Fraunhofer, instead of being effaced by the flame, was strengthened. The same held true with iron. The inference was of course drawn that sodium and iron were constituents of the glowing atmosphere of the Sun, and that light of the particular wavelength in passing through such an atmosphere was absorbed. This particle has been formulated by Miss Clerke as follows: Substances of every kind are opaque to the precise rays which they emit at the same temperature; that is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. But it does not follow that cool bodies absorb the rays which they would give out if sufficiently heated. Hydrogen at ordinary temperature, for instance, is almost perfectly transparent, but if raised to the glowing point, as by the passage of electricity, it then becomes capable of arresting, and at the same time of displaying in its own spectra, light of 4 distinct colors. In these few words we have the essence of spectroscopic chemistry and astrophysics. Materials of the Earth when heated to incandescence give a bright line spectrum characteristic of the individual element, but the same materials in the Sun show a spectrum marked by dark lines. While spectrum analysis was applied to chemistry and terrestrial materials by Bunsen, Kirchhoff worked industriously and made a map of the solar spectrum some 8 feet in length, in which the various lines of the elementary bodies were represented. The spectroscope, as constructed by Kirchhoff, consisted of a slit placed at the principal focus of the convex lens to make the rays parallel for their passage through the prism. In order to secure greater dispersion, several prisms were added and the emerging beam was passed through the telescope to form an image of the spectrum. The new instrument at once presented an enormous number of lines for study, not only of the Sun, but of various other celestial bodies. It was soon applied to the observing end of an astronomical telescope, so that the celestial image was formed directly at the slit of the spectroscope. By increasing the number of prisms, the dispersion of the spectroscope can be increased, and a longer spectral band produced, in which otherwise closely adjacent lines are increasingly separated. But in passing through a number of prisms there is considerable loss of light by reflection and absorption, so that a limit is soon set to the number of prisms employed. Another form of spectroscope, which makes use of a grating or a number of fine lines ruled very closely together on a transparent or a reflecting surface, has been found to possess greater dissolving power without any accompanying loss of light. In fact, the resolving power of a perfect grating depends simply upon the total number of lines it contains, so that the light efficiency per unit area may be as great for a large grating as for a small one. The principle of the grating depends upon the interference of the various minute light waves caused by a series of lines, amounting to from 10 to 20,000 to the inch, ruled on a transparent or a reflecting surface. The mathematical discussion of the formation of a spectra by the interference of the light waves in passing through or being reflected from such a grating can hardly find a place here. The result, however, is essentially the same as in the case of a prism. As soon as the dispersion of light was obtained by this means, it was found that it could be studied quantitatively, and that the grating could be used for astronomical measurements with as great facility as the prism spectroscope. Lewis M. Rutherford of New York was able to make excellent gratings about 1864, but it remained for Professor Henry A. Rowland (1848 1901) at the Johns Hopkins University to construct a dividing engine with a screw, practically free from error, which would move a small plate of polished speculum metal by regular intervals of 1/15,000th of an inch under a diamond point which traced sharp and regular lines. This machine not only was remarkably sensitive in its action, but automatically compensated for any minute irregularities in the screw. It was made to work at a constant temperature. It automatically proceeded with its ruling night and day until a grating of the desired length was completed. Professor Rowland for the first time ruled gratings on concave surfaces, and used them in place of the prism of the ordinary spectroscope. The spectra obtained with these diffraction gratings, in conjunction with special lenses, were many feet in length, and could be photographed in sections on photographic plates, each of about 20 inches in length. The grating spectroscope has been modified by Professor A. Michelson of the University of Chicago, who has devised a new form of grating in which a series of glass plates precisely equal in thickness are placed one on another like a flight of steps. A parallel beam of light, when transmitted through them, is resolved into spectra of a very high order, exceeding even those of Rowland's largest gratings, so that compound lines in the spectrum can be studied with facility. The application of the spectroscope has made of astronomy an experimental science, with methods and instruments for research and future progress fully as promising as may be found in any of the physical or natural sciences. The spectroscope has not only amplified astronomy, but it has developed the new science of astrophysics, in which astronomy is combined with physics. New methods and instruments for research already have brought to light striking discoveries which have compelled the modification of older astronomical and cosmical theories. In connection with the spectroscope it is possible to measure the temperature of the radiations sent out from the Sun and the stars with a high degree of accuracy by means of the bolometer, a sensitive thermometer invented by Professor S. P. Langley. It consists of two very fine threads of platinum wire about 1/2500th of an inch in thickness, mounted side by side within a constant temperature chamber. On one of these wires the radiation is permitted to fall, while the other is carefully shielded. Any change in the temperature of the wire on which the light or heat waves fall produces a difference in its electrical resistance that can be measured with a high degree of precision, so that a difference of less than 1/1000th of a degree in the temperature can be clearly indicated. The spectrum formed by the spectroscope is caused to move slowly across the exposed platinum wire of the bolometer, and a galvanometer in the circuit reflects from its mirror a spot of light upon a photographic plate, so that the deflections of the magnetic needle are photographed and registered, thus indicating the intensity and energy at the different parts of the spectrum. This instrument was first used by Langley to determine the amount of heat received from the Sun on the top of Mount Whitney in 1881, and since that time it has been employed by him and his successors at the Astrophysical Laboratory at Washington and also at Mount Wilson. The problem that the bolometer seems capable of solving is to determine the atmospheric absorption of light and heat in the passage of the Sun's rays to the Earth. It has also been used to measure the heat spectrum of the Moon and some of the brighter stars, in the case of the former showing that the Moon is very cold, as there is a considerable quantity of heat radiated having a wavelength greater than that of the heat radiated from a block of ice. After the fundamental work of Kirchhoff in identifying the spectral lines of the Sun and the stars with various terrestrial materials, it was but natural that the composition of stars as shown in their spectra should be thoroughly attacked by astronomers. Among the first of these was Sir William Huggins, who devoted the greater part of a useful scientific life to research of the heavenly bodies, especially as revealed by the spectroscope. In 1862 Huggins, Secchi, and Lewis M. Rutherford began their researches in stellar spectra that enabled them to classify and compare the spectral bands furnished by the different stars. It was the spectroscope in the hands of Sir William Huggins that made possible the solution of the riddle of the nebulae, the nature of which for long years had been a vital point of discussion among astronomers. On August 29, 1864, directing his spectroscope to the planetary nebulae in Draco, Huggins saw, instead of the bright band he anticipated, a single line which subsequently was resolved into 3 lines. Thus he proved that the nebula was not an aggregation of stars or incandescent solid materials, which would have afforded a continuous spectrum crossed by dark bands and a luminous gas. The effect of the spectroscope on astronomical research is thus summarized by Professor Hale. In astronomy, the introduction of physical methods has revolutionized the observatory, transforming it from a simple observing station into a laboratory. The interest of the students of astrophysics is no longer confined simply to celestial phenomena. For astrophysics has become, in its modern aspect, almost an experimental science, in which some of the fundamental problems of physics and chemistry may find their solution. The stars may be regarded as enormous crucibles, in some of which terrestrial elements are subjected to temperatures and pressures far transcending those obtainable by artificial means. In the Sun, which appears to us not merely as a point of light like the stars, but as a vast globe whose every detail can be studied in its relationship to the general problem of the solar constitution, the immense scale of the phenomena always open to observation, the rapidity of the changes, and the enormous masses of material involved provide the means for researches which could never be undertaken in terrestrial laboratories. Hence it is that astrophysics may equally well be regarded as a branch of physics or as a branch of astronomy. The great advantage of the spectroscope over the eye or the direct image from the photographic plate is its ability to analyze the action of light. While the intensity of light suffers in its journey through space, yet the nature or character of the light undergoes practically no change, so that the light from a distant star, separated from the Earth by an interval that seems to us almost infinite, can be received in our spectroscope and be resolved into a spectral band with difficulty but slightly greater than that which would be found in the employment of a luminous source of light at the opposite end of the laboratory table. The spectroscope, therefore, can be used in astronomy to determine the composition of a distant body according to the principle of spectrum analysis. But this is not all. It also enables the determination whether the light from a luminous body in the heavens is approaching or receding, and whether the light emitted from such a body is the same today as it was yesterday or half a century ago, and whether it comes from one or more bodies which the eye and perhaps the telescope cannot separate, but which are distinctly separate. Hence the astronomer is only too glad to remove the eyepiece from his telescope and put in its place some spectroscopic device which will analyze the light into separate colors and give him much valuable information as to the constitution and motions of even the most distant star. The value of the spectroscope is greatly increased by the application of photography. The general nature of a spectroscopic investigation can best be described by abstracting from Professor Hale its description of solar spectrum analysis. Sunlight must be reflected from a mirror to a heliostat, driven by clockwork to maintain the beam in a fixed direction, to the slit. Between the slit and the heliostat a lens is introduced, for the purpose of forming an image of the sun upon the slit. When the illumination is secured in this way, the whole grating is filled with light from the diverging rays. The grating then produces an image of the solar spectrum upon the photographic plate, where it may be recorded by giving a suitable exposure. To facilitate an accurate comparison, the solar spectrum is photographed side by side on the same plate with the spectrum of the substance whose presence in the Sun is to be determined. In order to accomplish this, one half of the slit is covered and the sunlight is admitted through the other half. Thus the solar spectrum is photographed on one side of the plate. After this exposure is completed, the sunlight is shut off, and the screen in front of the slit moved so as to cover the half previously open and to uncover the other half. The image of the Sun on the slit of the spectroscope is then replaced by an image of an electric arc light burning between two poles of iron. The spectrum of the iron vapor is thus produced on the plate, and a strip of this spectrum is photographed beside the strip of solar spectrum. The bright lights of iron are represented in the solar spectrum by corresponding dark lines which accurately image them in position. In Rowland's work on the solar spectra, thousands of lines were found to correspond with the iron lines given by the electric arc. The same process can be employed to determine the presence of other substances in the Sun. In the case of metals, the electric discharge may be caused to pass between two metallic rods, or fragments of the metal may be placed in a hole drilled in one of the carbons of an ordinary electric arc lamp. In the latter case the spectrum of carbon, and also of impurities which the carbon poles always contain, will appear on the plate with the spectrum of the metal in question. But these extra lines may always be identified and usually give no trouble. The identification of the solar lines, however, is not always so simple as in the case of iron. Many substances are doubtfully represented in the Sun by only a small number of lines, and it is sometimes very difficult to decide whether a few apparent coincidences are sufficient to warrant one in drawing definite conclusions. The matter is usually determined by ascertaining whether certain well-known groups of lines, which for various reasons are considered to be especially characteristic of an element, are actually represented. If these groups are absent, an apparent coincidence with certain less characteristic lines belonging to the same element should be regarded with suspicion. In the case of gases, the comparison is effected by the aid of vacuum tubes, in which the gas, usually at low pressure, is illuminated by an electric discharge. Thus the lines given by a hydrogen tube in the laboratory have been shown to coincide in position with lines ascribed to hydrogen in the Sun. After many years of study of the solar spectrum by these methods, Rowland reached the conclusion that the chemical composition of the Sun closely resembles that of the Earth. Certain elements, such as gold and radium, iodine, sulfur and phosphorus, chlorine and nitrogen, have not been detected in the Sun. But this does not prove that they are certainly absent, as their level in the solar atmosphere, or in the low degree of their absorptive effects, might prevent them from being represented. On the other hand, various substances not yet found on the Earth are shown by many unidentified lines of the solar spectrum to be present in the Sun. Some, if not all of these, will probably be discovered by chemists, just as helium was found by Ramsay in clevite. Rowland remarked that if the Earth were heated to a sufficiently high temperature, it would give a spectrum closely resembling that of the Sun. End of section 4.